On the homework, there was a question regarding the circle of Willis. So I wanted to go through that with you guys one more time. So the basilar artery brings blood into the posterior part of the brain, where the internal carotid arteries bring blood towards the middle portion. The circle of Willis is what is connecting these. So we have this first part here of the posterior cerebral artery, and then that's on both sides, and then we continue anterior using this posterior communicating artery, and then we continue forward using the anterior cerebral artery, and finally what closes the circle here is this anterior communicating artery. So the vessels that are highlighted in yellow, anterior communicating artery, anterior cerebral artery, the posterior communicating artery, and the posterior cerebral arteries are the ones that make up the circle of Willis itself. The basilar as well as the internal carotids are two vessels that provide blood to the circle but are not necessarily part of the circle. Although in some texts, the internal carotid artery can be listed as part of the circle of Willis. For the purpose of our class, I would like you to focus on the four vessels that are listed here as being the actual part that forms the circle of Willis itself. The next question I wanted to go over with you had to do with the different types of vessels, arteries in particular, their lumen size, and what was in the wall. So for example, we'll talk about elastic arteries. In their wall, it's more elastic. That is because you want it to be very distensible. It has to go with pressure surges. So if we look at the image down here, we can see that in the proximal aorta, as well as the large arteries, there are these huge pressure swings. We can see these large pulsations. They go from, in this case, 80 millimeters of mercury to 160. So there are these huge pressure surges, and that's causing the wall to distend out. Every beat when the heart ejects blood out, and then between beats, it's going to recoil back in. And when it recoils back in, it's going to do what we call maintain forward flow between beats. What that means is when the heart ejects blood, and we're going to see this in this red line down here, rising, the vessel walls of the artery is pushing out. That's because it's very elastic. Then when the heart begins to relax, show the pressure dropping back down, hits that dicrotic notch and continues to go down, the vessel walls are going to recoil back in. And when it recoils back in, what's happening is the blood that's in here is going to drive forward and continue to be driven out towards the body while the heart is filling and waiting for the next beat. So now I'd like to address the muscular arteries. Muscular arteries have more smooth muscle here in the wall. Doesn't look like more because they're smaller, but in total, compared to the distance across the lumen where the blood is, the amount of tunica media is actually proportionally much larger than it is in the elastic artery. So muscular arteries have more muscle in the tunica media per lumen size. That means for how big the hole is that blood goes through. So there's actually more muscle in the wall that's affecting the radius or diameter of the actual lumen size. This is really important because it is these muscular arteries, and even the smaller ones, muscular arterioles. So we're just going to combine these two together, and what we see is a reduction of our pulsations. They're not as boingy as they were over here with the elastics. We're actually tempering down the pulsations before we get to the important parts of our body. And so the smooth muscle helps to dampen the pulsations, but what's also important is the smooth muscle also can cause the vessel to dilate or constrict. So muscular arterioles have a greater ability to vasoconstrict or vasodilate. If we constrict, we're going to increase blood pressure. If we're going to dilate, we're going to decrease blood pressure. So muscular arteries have a greatest impact on our blood pressure. The other thing they also do is they dampen pulsations. So they allow for huge pulsations that enter these muscular arterioles to steady out, and actually so that way our organs don't get these high surges of pressure. I also wanted to talk to you about blood flow. Which of the factors that's listed in this equation that was presented in our lecture has the greatest impact? So we've talked about the change in pressure, that's delta P. We have in red how long the blood vessel is. And then we have in blue the viscosity of fluid. Is the fluid really liquidy or is the fluid really sludgy? They all impact the ability of flow to go through a vessel. But the most important one is the radius of the vessel. And the reason why it is the most important is because it is to the power of 4. That is because any single change in the R is then exponentially increased to the power of 4. And none of the others are like that. They are more of a linear change. You increase the pressure, you're going to increase the flow by a linear amount. If you increase the radius a little bit, you're going to do it to the power of 4. So it has a much, much larger